Okay, so we talked about the direction of the correlation. Now let's talk about how the absolute value of the number is going to determine the strength. So what I mean by absolute value is when making the assessment of strength, you need to ignore that positive and that negative sign. A lot of times people, having been trained on number lines, have in their mind that negative numbers are by definition smaller than positive numbers. You've got to ignore that positive and that negative sign for the purposes of interpreting correlations, because all the sign is telling us is what the direction is. Are the two variables moving in the same direction, or are they moving in opposite directions? Is it a positive correlation and they both move in the same way, or is it a negative correlation where one increases while the other decreases? Now, let's talk about how do we determine how strong the correlation between the two variables is. The absolute value. So independent of the plus or the minus sign, if the value of the number is somewhere between 0 and a 0.2, we call that a zero correlation. Those two variables really aren't going together at all. Knowing the score on one of them is not going to help you at all to make a prediction about the other one. So here's an example of, we've got this is from New York City, the percent of students who are getting a free or reduced price lunch, and then here we have on the y-axis total school rating points, so like the quality of the school. And what you see is each of these little blue dots represents one school as far as how many students are getting free and reduced lunch, and then what the rating score is. And what you'll notice is those blue dots are sort of randomly distributed around the picture. This is a negative 0.6. You can see that the line of best fit, where'd my arrow go? There it is. The line of best fit is this little line this is what actually the correlation coefficient does for us, is it calculates where this line would be placed so that all the dots are equidistant from that line. So the correlation coefficient calculation produces the slope of this line. It tells us the value of that line. Okay, what you can see is that to get the line of best fit, really this line is practically flat. It's practically parallel to the x-axis. If it is parallel to the x-axis, it's going to be just a zero correlation. This one's slightly tilted downward, so we're getting the 0.06, and it's slightly tilted downward, so we're getting the negative 0.06. It's really, there is no association between how many kids are getting the free and reduced price lunch and then the quality rating of the school is basically what this chart's showing us. All right, now here's an interesting thing to keep in mind. Correlations can really only assess what are called linear relationships. This is a linear relationship. Linear means we could fit a line in here and it would be equidistant from the dots. This is showing us patterns of data that would come out as zero correlations, but can you imagine if you got one of these patterns? That would look meaningful to you. If you saw, for example, that at the lowest percentage of kids on free and reduced lunch, we had the highest school ratings. And then at this mid-range of free and reduced lunch participation, we have the lowest school ratings. Then at the mid-range of mid-range of free and reduced, so we're at like 50% of the kids are getting free and reduced lunch. So this is like nobody's getting free and reduced lunch. 25% are. 50% are. Now we're back up to great performance. Here we are at 75% are getting free or reduced price lunch, and we're getting terrible school ratings. And then up here we've got 100% are getting free and reduced lunch, and we've got great school ratings. That would be meaningful, right? That'd be like, okay, something's going on. But a correlation coefficient is looking for one line to fit through here, and it would come to the conclusion that the best line would be right here parallel to the x-axis. It would conclude that there was nothing interesting going on. Same thing here. I mean, look at this nice X. Something's going on where you get your high and your low scores on the y-axis being associated with the lowest scores on the x-axis, and high and low scores on the y-axis being associated again with the high scores on the y. This is interesting, but a correlation coefficient wouldn't reveal it. It would give us zero. For any of these patterns, we would get a zero. So this is one of those cases where it's really important for the researcher to know what the actual pattern of the data looks like, and then realize this is not the kind of data that you should be analyzing using a correlation coefficient. This is the kind of thing that the alternates, things that the other kinds of data analysis that you could conduct, you'll learn in grad school. This is like really complex statistics that you would have to learn in order to analyze these kinds of patterns. Okay, the next level of strength would be the 0.2 to 0.4. We call this a weak correlation, and I have to tell you, in psychology, a lot of our correlations are this sort of weak correlation. Now up here I've reported what the R is, the correlation coefficient. It's a negative 0.24. And you can see that our line of best fit is going down to the right. So it shows you that higher scores on the y-axis are being associated with lower scores on the x-axis, and higher scores on the x-axis are being associated with lower scores on the y. But it's pretty weak. I mean, there are outliers here, ones that are making this really uninterpretable. The line of best fit goes here, but it's really, one needs to be very careful about interpreting this data. This number here, this r squared, is the little r squared, and it's actually telling us how much of the variability can be accounted for by this data. And so what it's showing us is for the length of the year that the empire was founded, and then how long it lasted. Really only about, well, if we round up, about 6% of the variability between empires can be attributed to the time when it was founded. I mean, that's not very, 6% of the variance is being accounted for. That's not very much. So we could say that's very weakly related. Okay, so now I have something that comes out of psychology, Palm's negative mood score. This is a scale that you can take that produces a particular score, and then it's being tied to something physical, how much oxygen's being carried on your hemoglobin. This is what we call a moderate correlation. What you're seeing is that the outliers that do exist are closer to the line of best fit. You have fewer of those really crazy outliers that you saw in the last picture. So now we have an R of it's negative, but 0.56. So this is what we call a moderate correlation. If we get something this strong in most psychological tests, we're pretty happy with it. I mean, this, again, if we square it, we're accounting for about 25% of the variability in the scores. So it's moderate. We're usually pretty happy with it. We're delirious if we could get something this strong, which we usually don't get in psychology. I had to go to sort of biological stuff to get this demo. This one's water and sanitation, access to an improved water source, and then this is children's health, infant mortality rate. So the more healthy water they had, the lower the mortality rate. The less access to healthy water, the higher the infant mortality rate. And again, I don't know how come all my examples came out negative, but I've got a negative 0.73 as the correlation coefficient. About 53% of the variability is being accounted for by about 53% of the variability in children's mortality is being accounted for by knowing whether they have access to a water source. So it's this is a strong correlation, and we're still only accounting for about 53% of the variability based on that one thing. Now this one, to find something that's very strong is really hard, and I have a sneaking suspicion it wouldn't have been as strong except for this number right here. This little dot right there is what's making this correlation a 0.91. This is the correlation between the average years married from 18 to 44 for white women and then Bush's share of the vote. So it's a pretty crazy correlation that's been made here. So what you're seeing though is, notice that there's a lot more variability up here, but this guy's sort of anchoring us. And so the line of best fit is, I finally found a positive one, didn't I? Line of best fit is going up and to the right, and there aren't very many outliers. But these numbers here might have given us a slightly lower correlation if it weren't for this guy being in the right plane, I guess would be the right word, to be continuing this line as it is. Now you'll notice R squared is 83%. So about 83% of the variability in who the person voted for could be accounted for by how long they'd been married. So strange thing to be correlating, but it came out pretty strong. Like I said, generally in psychology, we are pretty happy if we can get a weak to a moderate. If we get moderate, we're like, oh my gosh, we're so smart. We've got so much of this accounted for. We're completely jazzed if we can get a moderate correlation. Now, to put this into a little bit of context, the correlation between whether a person smoked and whether they develop lung cancer is a 0.3 correlation. The correlation between whether a person does reliable breast cancer self-exams and whether they catch the breast cancer when it's still small is a 0.2 correlation. So things that we think of as being very strongly correlated, things that we think of as explaining a lot of the variability in real life, it turns out are pretty weak to very, maybe even into the zero area of correlations. So we don't need to be feeling embarrassed that psychology tends to have weak to moderate correlation coefficients. We just have to be wary whenever we hear correlations that when it comes out significant, that doesn't necessarily mean that the correlation was strong. It just means that for this sample, it achieved the level of significance. I will explain what significance means more in another chapter. All right, now what I'm going to do is take a little break because we're going to need the whole segment to talk about why correlation does not equal causation.